The process begins with detailed engineering, where precise specifications and dimensions are determined. Next, high-quality steel plates are delivered to the manufacturing site. The steel plates are then rolled into cylindrical shapes. After rolling, tack welding is performed to hold the rolled plates in place. This step ensures the sections are correctly shaped before the final welding. Following tack welding, the longitudinal welding process begins. This involves welding along the length of the cylinder, creating a strong and seamless joint. This welding is critical for the structural integrity of the monopile. Once welded, the individual cans, cones, and sections are transported to Maasvlakte 2, a specialized port facility. Positioning, tack welding, and circumferential welding at Maasvlakte 2, the sections are positioned accurately, and tack welding is performed to hold them in place. Circumferential welding then joins these sections together, ensuring a robust and continuous monopile structure. The assembled monopiles undergo rigorous testing to verify their structural integrity and compliance with engineering standards. Finally, the monopiles are coated in a specialized coating hull. This protective coating prevents corrosion and enhances the durability of the monopiles, ensuring a long service life in the harsh marine environment. The construction begins with pitching the bottom tubular pile. This involves positioning the first section of the steel tubular pile at the desired location. Precision is crucial at this stage to ensure the pile is correctly aligned both vertically and horizontally. Specialized cranes or lifting equipment are typically used to handle these heavy and large diameter piles, ensuring they are securely and accurately placed before the pressing begins. Once the bottom pile is in position, the gyropressing process starts. Gyropressing is a method where hydraulic jacks apply downward pressure and rotational force to drive the pile into the ground. This technique reduces noise and vibration compared to traditional pile driving methods. The rotational movement helps the pile penetrate through various soil layers, including those with high resistance. Gyropressing ensures the pile is embedded firmly into the ground, providing the necessary load-bearing capacity. After the bottom pile section is partially or fully embedded, the next section, upper pile, is pitched. This involves aligning the new section of the tubular pile with the already installed bottom section. Proper alignment is critical to maintaining the structural integrity of the pile. The upper pile is typically welded or connected using flanges or couplers to the bottom section to create a continuous, robust pile shaft. With the upper pile in place, the gyropressing process resumes. The hydraulic jacks again apply pressure and rotational force to drive the newly added section deeper into the ground. This process is repeated, section by section, until the pile reaches the required depth or hits a predetermined layer of bedrock or dense soil. The gyropiler, equipped with tracks or wheels, is designed to move itself to the next pile location. This self-moving capability enhances efficiency by reducing the need for additional lifting equipment or manual repositioning. The gyropiler relocates along a predefined path, which is crucial for maintaining the planned layout of the pile foundation. For particularly challenging soil conditions or when additional driving force is required, a driving attachment may be pitched. This attachment, connected to the top of the tubular pile, provides extra impact or vibratory force to assist in driving the pile deeper. The driving attachment ensures that the pile can penetrate through tough soil layers or reach the necessary depth for optimal load-bearing capacity. The pile installation process is considered complete once the pile reaches the predetermined depth and is adequately embedded in the ground. Final inspections are conducted to ensure the pile is correctly positioned and structurally sound. Any necessary adjustments or reinforcements are made at this stage. The top of the pile is then prepared for the next phase of construction, which may involve capping, connecting to a pile cap, or integrating into a larger foundation system. The accuracy of each item in the manufacturing process is of the utmost importance to ensure the overall quality and functionality of the transition pieces. Precise positioning of secondary steel components, such as platforms, boat landings, and ladders, on the large steel tubular structures is crucial. This precision guarantees that all parts fit correctly and perform their intended functions without issues. Highly skilled welders perform the welding with attention to detail, adhering to stringent standards to ensure strong and reliable joints. Each weld undergoes thorough inspection by an external specialist to confirm its integrity. This rigorous quality control process prevents potential failures and ensures the structure's durability in demanding offshore environments. Accurate application of the multi-layer special coating is also essential, as it protects against corrosion and extends the lifespan of the structure. The assembly of the transition piece is a process that begins with the arrival of secondary steel components and large tubular structures at the Hoken yard. Each secondary component, including platforms, boat landings, ladders, and other functional elements, is precisely positioned on the large steel tubular. Highly skilled welders then join these components, ensuring each weld meets the highest standards of quality and durability. Once the welding is complete, an external specialist rigorously inspects each weld to confirm its integrity. Following the welding phase, a multi-layer special coating system is applied to the entire structure. Thoroughly clean the pipe ends to remove any debris, then evenly apply lubricant to ensure smooth insertion and a tight seal. Slide the pipe coupling over the larger pipe up to the marked depth. Lightly tighten the pipe coupling on the larger pipe so that it can still be rotated. Slide the smaller pipe into the pipe, coupling up to the marked depth. Using a screwdriver or appropriate tool, gently tighten the strap around the pipe. Ensure it is snug enough to hold the pipe in place, but still allows for slight adjustments if necessary. For couplings equipped with tension locks, use a wrench to alternately tighten each lock. This ensures even pressure distribution and a secure fit, preventing leaks and maintaining the integrity of the connection. Using a torque wrench, evenly tighten both tension locks to 15 Newton meters to ensure a secure and reliable pipe connection. While above-ground basins are the most cost-effective method for stormwater detention, underground systems are often necessary when land space is limited. These underground systems are typically installed beneath parking lots, parks, or sports fields. CMP is favored for these applications due to its wide range of sizes, corrugations, coatings, and gauges. It offers both solid pipe detention and perforated pipe infiltration options, with extensive fittings and customized customizable layouts, ensuring ease of handling and quick installation. The installation process begins with a detailed submittal of pipe materials and guidelines, reviewed and approved by an engineer. A pre-construction meeting with the contractor and local sales engineer ensures all details are understood. Pipes are carefully unloaded using appropriate equipment and placed on a prepared granular foundation. For solid pipe systems, neoprene gaskets and corrugated bands secure the pipes. Proper backfill and compaction are critical, using equipment such as small excavators and vibratory heads to ensure stability. In perforated pipe systems, non-woven geotextiles encapsulate the excavation to prevent soil migration. Stone backfill, without fines, is used to maintain void spaces for storage. Proper alignment and compaction ensure the system's integrity.
The first step in installing a stormwater treatment system is preparing the excavation pit. This involves clearing the construction site and digging a pit to accommodate the system. The pit's dimensions should align with the specifications provided by the manufacturer. Once the excavation pit is ready, the stormwater treatment system components, including the SediPipe L+ units, are delivered to the construction site. Careful planning is essential to ensure timely delivery and efficient storage of the components. Adequate space is allocated for storing the materials, minimizing the risk of damage or obstruction to the construction process. Installation of SediPipe L+ beginning at the target shaft and outlet set. The installation process commences with setting up the target shaft and outlet. The SediPipe L+ units are positioned starting from the target shaft, which serves as the endpoint for treated stormwater. The outlet set is securely installed to facilitate the proper discharge of treated water. Each unit is connected in sequence, forming a continuous path for stormwater treatment. The sedimentation path typically consists of a series of channels or chambers, arranged in a sequence within the excavation pit. These channels are engineered to slow down the flow of stormwater, allowing gravity to facilitate the sedimentation process. As runoff enters the sedimentation path, its velocity decreases, enabling heavier particles, such as sediment, debris, and pollutants like tire wear and oil, to settle to the bottom. To optimize sedimentation, the path may incorporate features such as baffles, weirs, and settling basins. Baffles are strategically positioned to induce turbulence, promoting particle settling, while weirs help regulate the flow of water through the system. Settling basins provide additional space for sediment accumulation, preventing it from re-entering the water stream. Furthermore, the sedimentation path may include filtration elements, such as sediment traps or screens, to capture finer particles and prevent them from escaping into downstream systems. These filtration mechanisms enhance the effectiveness of the sedimentation process, resulting in cleaner water output. Throughout installation, careful attention is paid to ensure proper alignment and sealing of the sedimentation path components to prevent leaks or bypassing of untreated water. The start shaft, often constructed from durable materials such as concrete or high-density polyethylene, HDPE, serves as the initial receptacle for incoming stormwater. Its design typically incorporates features to facilitate the smooth flow of runoff into the treatment system while preventing debris and contaminants from entering. The shaft's dimensions are carefully calculated to accommodate the anticipated volume of stormwater and ensure optimal performance. At the top of the start shaft, the inlet set is installed to capture runoff from various sources, such as paved surfaces, rooftops, or open ground. This set of components is strategically positioned to intercept stormwater efficiently, minimizing the risk of untreated runoff bypassing the treatment system. Inlet structures may include grates, catch basins, or curb openings, depending on the site's topography and drainage characteristics. Grates or mesh screens are commonly employed to filter out larger debris and prevent blockages within the start shaft. These components help maintain the integrity of the stormwater treatment system by reducing the risk of clogging and ensuring continuous operation. Additionally, inlet structures may incorporate features such as sumps or sediment traps to capture sediment and prevent it from entering the treatment process. Proper positioning and alignment of the start shaft and inlet set are crucial to ensure the efficient capture and conveyance of stormwater into the treatment system. Construction teams meticulously measure and level the components, taking into account factors such as slope and hydraulic efficiency. Sealants or gaskets may be applied to joints to prevent water leakage and maintain system integrity. Finally, extension pipes are installed to complete the stormwater treatment system. These pipes connect various components, allowing for seamless flow and functionality. Extension pipes may be adjustable to accommodate variations in terrain or specific project requirements. The process of manufacturing steel arch profiles for K-span technology begins with the selection of high-quality steel materials. These materials undergo rigorous testing and quality control measures to ensure optimal strength, durability, and performance. Once the steel is sourced and prepared, it is fed into a specialized rolling and bending line, where it undergoes a series of precise forming operations. The rolling and bending line utilizes advanced machinery and computer-controlled processes to shape the steel into precise arch profiles, according to the desired specifications. This process involves the gradual bending of the steel, guided by sophisticated algorithms and engineering principles, to achieve the desired curvature and dimensions for each arch segment. The accuracy and consistency of the forming process are critical to ensuring the structural integrity and stability of the assembled arch halls. One of the key advantages of K-span technology is its efficiency and speed of construction. The self-supporting nature of the arch profiles eliminates the need for internal support structures or secondary framing components, streamlining the assembly process and reducing construction time and costs. Additionally, the modular design of the arch profiles allows for easy transportation and assembly on-site, making it ideal for projects in remote or challenging locations. The versatility of self-supporting assembled arch halls, built with K-span technology, makes them well-suited for a wide range of applications. These structures are commonly used for industrial facilities, warehouses, storage buildings, agricultural barns, sports arenas, and exhibition halls, among others. Their spacious interior layouts and open-span design provide ample space for various activities and operations, while their robust construction ensures long-term durability and reliability. Furthermore, K-span technology offers flexibility in design customization, allowing architects and engineers to tailor the dimensions, configurations, and aesthetic elements of the structures to meet specific project requirements and preferences. Whether it's incorporating additional features such as windows, doors, mezzanine levels, or insulation systems, K-span arch halls can be adapted to suit diverse functional and aesthetic needs. Prepare the site. Begin by excavating a trench according to the design specifications provided by the engineer. The trench should have a smooth and level bottom to accommodate the easy flow pipe properly. Ensure that the trench is wide enough to comfortably accommodate the easy flow pipe and allow for proper backfilling. Inspect the pipe. Before installation, inspect the easy flow pipe for any damages or defects. Ensure that the pipe is clean and free from debris. Check the connections and fittings for any signs of damage. Lay the pipe. Carefully place the easy flow pipe into the trench, starting from the lowest point of the septic system and working upwards. Position the pipes with the perforated side facing downwards to allow for proper drainage. Make sure the pipes are aligned correctly and have a slight downward slope to facilitate the flow of wastewater towards the treatment area. Connect the pipe. Connect the easy flow pipes using appropriate fittings and connectors. Ensure that the connections are secure and watertight to prevent any leaks. Use manufacturer-recommended adhesive or sealant to seal the joints properly. Backfill the trench. Once the pipes are in place and properly connected, backfill the trench with suitable backfill material such as gravel or sand. Fill the trench in layers, compacting each layer thoroughly to provide adequate support for the easy flow pipes and prevent settlement. Install inspection ports. Install inspection ports at strategic locations along the easy flow pipe to facilitate future maintenance and inspection of the septic system. These ports will allow easy access to the system for monitoring and troubleshooting purposes. Test the system. After installation is complete, conduct a thorough inspection of the entire septic system to ensure everything is in proper working order. Test the system by running water through the pipes to check for any leaks or drainage issues.